This is the first of three sections about the product operator method for describing NMR experiments, and in a way this is really the heart of the course. It's the technique that you're going to need in order to be able to describe modern multiple pulse experiments. Now, the product operator method is a quantum mechanical method in contrast to the vector model, so it provides a complete description of pulsed NMR experiments. So it will not have the limitation that the vector model had. In other words, we will be able to describe scalar coupled systems, multiple quantum, and so on. And the product operator method is very well suited to multiple pulse NMR on spin half systems, which is what we're going to consider. So it really does turn out to be a very useful tool in that context. Although I'll describe to you sort of the background of it, when you come to use the product operator method, it really does boil down to applying a set of rules. And so that's actually quite convenient, and many of those rules can actually you can think of with a geometric interpretation. So actually it turns out to be quite similar in many ways to the vector picture. So although it's based in quantum mechanics, once you get the hang of it, I hope you'll find it's reasonably intuitive to use. Now, what we're going to do in this first section is we're going to look at one spin system, and that's so we can get used to the notation and the language. And it also means that you can compare any result you get with what you would expect from the vector picture. So you can always fall back on the classical picture and check to see what you're getting is correct. And as we go through the examples, I'll constantly refer back to the vector system, a vector model, and say how that would predict the same thing. The only thing that we've not including here is relaxation. Relaxation is not included in this, so all our free induction decays will last forever as they did in the vector picture. So how does it work? Well, when we talked about quantum mechanics the first time, I said that all the information about the system is contained in the wave function, and that's certainly true. In this theory, the product operator theory, all the information about the system is contained in a slightly different object, which is related to the wave function, but it goes by the delightful name of the density operator. And I'm going to give it the symbol rho, and it has a hat on it to remind you that it's an operator. So calculation of the density operator is tantamount to calculating all of the possible properties of the system. So that's what we're going to do. For a one-spin system, you can always express the density operator as a linear combination of the operators Ix, Iy, and Iz. Now let's unpack that a little bit. Linear combination means it consists of a part of Ix, a part of Iy, and a part of Iz. And that's what's written here. There's an amount Ax of the operator Ix, there's an amount Ay of the operator Iy, and so on. And these are just numbers, and these numbers or coefficients will vary over time, and that's why it says bracket t after them. Now what about Ix, Iy, and Iz? Well, we've already come across Iz. That represents the z component of spin angular momentum. And you won't be surprised to discover that Ix and Iy represent the x and y components of the spin angular momentum. So these are three operators that represent the x, y, and z components of the spin angular momentum. And the density operator can always be expressed as some combination of these, some linear combinations as it's called. Now these coefficients, Ax, Ay, and Az, they're just numbers, and they vary with time, and that's really what we're going to calculate. And the thing that's really useful about this theory is the interpretation of what you get. So when we do a calculation, at some point we'll end up with some expression. There'll be a certain amount of Ix, a certain amount of Iy, and a certain amount of Iz. And the question is, what does that mean? And what that means is something very simple. The amount of Ix is the X magnetization. The amount of IY is the Y magnetization, and the amount of IZ is the Z magnetization. So for example, you could say that if the coefficient of the X operator is AX, that means the amount of X magnetization is proportional to AX. The amount of Y magnetization is proportional to AY, and so on. Now there's some constants of proportion in there which have all sorts of physical constants in them which are of no consequence to us. So we'll just assume that the X magnetization is equal to this coefficient, and that's perfectly okay. So the nice thing about this is that when we do the calculation of the density operator, we can just look at it and I can say, if that density operator is IY, that means the magnetization is along Y. If that density operator says IX, it means the magnetization is along X. So the real beauty of this theory, and the reason it's been so successful, is that you can always interpret the result very quickly in terms of the observable things, the X, Y, and Z magnetization. Now, everything we need to know is in the density operator. So the crucial thing is, how are we going to actually calculate what the density operator is? And in particular, we need to realize that the density operator varies with time. So if you think about during a free evolution, the magnetization is going round and round and round, the X and Y components are oscillating, and that means that the density operator must also be changing with time. So we have to write it as rho t. So that's what we've got to try and calculate. And in fact, in this theory, there's a straightforward way of calculating what the evolution of the density operator is going to be. So rho 0 is the density operator at time 0 at the start, and rho t is the density operator at the time t. And the rest of this, h is the Hamiltonian, which we've already come across, t is the time, and I is the complex I. And in order to work out what's going to happen, all we need to know is where we start from, what rho 0 is, and we need to know what the Hamiltonian is. And the Hamiltonian is different during pulses and delays, and I'll explain that. And you may think this doesn't look very helpful, but as we will see, the solutions to this equation, this thing involving this triple product, they are already well known, right? That means somebody else has worked them out. And in fact, there's a limited number of these, and we already will know what these are. So in fact, solving this equation is actually very simple. It really is just a matter of looking up a solution from a table. So by using this kind of approach, we can calculate how the density operator varies with time, and then we can interpret what that actually means just by looking at the coefficients of Ix, Iy, and Iz. And you don't really need to worry too much about where this comes from or how it works. This is how you're going to use it. So first of all, let's have a think about the Hamiltonians, because we need to know the Hamiltonian to put it into that equation to work out how the density operator varies with time. So for free precession, that just means when you just leave it alone and the spins are just evolving under the influence of the static magnetic field, the Hamiltonian is omega, which is the offset, times Iz, which is this operator of the Z component of angular momentum. In fact, that's exactly the Hamiltonian that we wrote down for a single spin in a magnetic field right at the beginning. And in fact, we're going to do this in the rotating frame, so it's not the Larmor frequency, it's the offset. So that's the free precession Hamiltonian. If we apply a pulse about the x-axis, and I'm going to assume that all the pulses are hard, remember that means you can assume that to a very good approximation, the field is along x. We don't have to worry about this tilting of the field. Then the Hamiltonian for a hard pulse is little omega 1 times Ix. Right? Little omega 1 is the RF field strength that we talked about in the vector picture. And again, you shouldn't be surprised that it's times Ix, because you remember that a pulse is a field along the x-axis, whereas an offset is due to the field along the z-axis. If you want a pulse about the y-axis, it's not of any surprise you should find that the Hamiltonian is omega 1 times Iy, right, rather than Ix. So basically we can write down all these Hamiltonians, and the key thing is that the Hamiltonians, they are all written in terms of Ix, Iy and Iz, and the density operator is all written in terms of Ix, Iy and Iz. So everything is written in terms of these operators. So I said that we could work out what happens just by using this idea of the Hamiltonian and that expression I gave you. And I think the simplest way to do that is just to do an example so you can see how it actually works. So let's suppose that at time 0 the state of the system, the density operator, is Ix. Now immediately we can interpret what that means. What that means is that there's X magnetization, no Y magnetization, no Z magnetization. Right? Because if there was Y or Z magnetization, there'd be a term in Iy or a term in Iz. So at time 0, we've got pure X magnetization. The density operator is Ix. That's what that means. And I'm going to imagine that I'm going to let this precess freely. And so I need to know the free precession Hamiltonian. And I've just explained to you that that's capital omega Iz. So we know the Hamiltonian. And the equation we need to solve is e to the minus IHT, rho 0, e to the IHT. And we know h is omega Iz, and we know rho 0 is Ix. So all I've done on the second line is to substitute that in. Now you may be tempted to think that why don't I just squash the e to the IHT and the e to the minus IHT together, and that will give you e to the 0, which is 1. And you can't do that, and the reason you can't do that is that these are operators, and you can't reorder operators willy-nilly, right? You have to think very carefully about it. And in fact, you're certainly not allowed to shift the e to the IHT and the rho 0. You're not allowed to swap them over. So you have to preserve this order. So the problem then is, how are we going to solve this equation that's on the bottom line then? Well, I said that all of the solutions we need are already known, and if you get a book about the theory of angular momentum, and I'm sure you have one by your bedside, you will discover this equation: e to the minus I theta Iz, Ix, e to the I theta Iz is equivalent to cos theta Ix plus sine theta Iy. That is a well-known identity in the theory of angular momentum. Now, if you want to know where that comes from, we can talk about that another day, but these you just have to take as given. And if you look at this equation on the left-hand side of the identity, and on the right-hand side of the one I'm trying to solve, of course they're exactly the same thing. All I have to do is realize that if I replaced theta by omega t, then I would get exactly what I wanted, because what I'm trying to work out is written there on the bottom line. So what that means is that after time t, the density operator is cos omega t Ix plus sine omega t Iy. Right, now remember we started out with Ix, and we're allowing free precession for a time t. And what I've got is cos omega t times Ix and sine omega t times Iy. Well, of course, that's exactly what you would expect, because if you think about your vector picture, if I start out along x and I allow free precession for a time t, I will get an x component which goes as cos omega t and a y component that goes at sine omega t. So this is exactly what the vector picture would predict for you. Now you may think, of course, that's a very complicated way of getting something that you could do very simply with a vector picture. And of course that's right, but remember the reason for doing it like this is so that you can constantly compare the result of the vector picture with the result of your quantum calculation to verify that it's making sense. So we've written down this equation, we've solved it using this well-known identity, and it's given us a solution which we recognize as being definitely correct. So that's how you go about doing this. Now, writing all these things out gets incredibly tedious after a while, and especially you realize you constantly keep writing out e to the minus I blah blah blah, and then you write e to the plus I exactly the same. So there's a shorthand notation which is used for this, and that is where this rotation would be written as Ix on the left, that's the starting density operator, and then an arrow. And what you write over the arrow is the Hamiltonian multiplied by time. So remember, the Hamiltonian in this case is omega Iz. So the Hamiltonian times time is omega t Iz. And the thing on the right is the solution we just came up with. So this arrow notation we will increasingly use. And if you want to think of it in very general terms, the thing on the left of the arrow is a density operator at time 0. The thing on the right of the arrow is the density operator at time t, and the thing written over the arrow is the Hamiltonian times time. That's just a notation, but that's commonly used in this theory. So over the arrow is the Hamiltonian times time. It's common to forget the time factor. So if we think of this now in rather more general terms, the density operator and the Hamiltonian are all written in terms of Ix, Iy, and Iz. That's really the key to this theory. And so if you think of these equations, what we're always going to end up with are equations where we've got an operator Ia, which could be any one of x, y, or z, and an operator of IB, which could be any one of x, y, or z. We're always going to ultimately end up with trying to solve an equation like that. And all of these have already been solved for all possible values of A and B. And there aren't that many, of course, because A, B can only be x, y, or z. And in this table, here they all are. So look at the first line. It is e to the minus I theta Ix times Iy times e to the I theta Ix. And we would interpret that as a rotation of y about x, right? So the e to the minus I theta Ix means you're rotating through an angle theta about x, and the thing that's being rotated is the operator Iy, right? The second line, it's e to the minus I theta Ix Iz, right? So that is a rotation about x of the operator z. And that's what's listed in the second and third columns. And you'll see that they all give you exactly the same kind of result. They all give you cos theta plus sine theta times another operator. So all of these identities fall into a particular format. And in fact, the one we used just now is highlighted in red there. It's a rotation of x about z, and it was that e to the I theta Iz Ix operator that we used. So all of the possible ones you need are already on this slide. Now, you may think there are some missing. For example, one that's missing would be rotation of z about z, which would be e to the minus I theta Iz e to the I theta Iz. But that doesn't do anything, right? Because if you take z and you rotate it about z, nothing happens. So the result of this is just Iz. So rotation of z about itself has no effect. And in quantum mechanics, that's because Iz commutes with itself. So likewise, a rotation of x about x and a rotation of y about y, that has no effect. And again, if you think about the vector model, that makes absolute sense. If you've got the magnetization along x, and I apply an x pulse, nothing happens to it. And that's just saying the same thing quantum mechanically. So that just gives IZ. Now when you're doing a calculation, you need somewhere to start from, and you remember in the vector model we say we start with equilibrium magnetization. Equilibrium magnetization appears along the z-axis, so that means in terms of the density operator it would be represented by the operator IZ. Now there ought to be some kind of constant of proportion in there to take into account how many spins you've got and the temperature and the magnetic field and so on, but none of those things are really useful in our calculation. So what you normally do in these calculations is forget about that and just say that the starting density operator is IZ, just to forget about the scaling factor there. So we know where to start, we know how to write rotations for pulses and for delays, so we can now actually do a calculation with this and see how it's actually going to work. So the calculation I'm going to do is just the simplest possible experiment, which is the pulse acquire experiment. And I'm going to imagine that I do a pulse, and I'm going to make the pulse have a flip angle alpha rather than just making it 90 degrees, just to add a little bit more complexity. And then after the pulse, I'm going to just acquire the signal in the usual way. So, first of all, we've got to work out the effect of the pulse, and I'm going to imagine that the pulse lasts for a time Tp, and I've got the Hamiltonian for the pulse, which is the one along the x-axis. So we know what the Hamiltonian is. It's omega 1 Ix. That's the Hamiltonian for a pulse. And we know what the starting density operator is. That's just Iz. That's equilibrium magnetization. So if I plop that into that equation, I get the following. So I get e to the I omega 1 Tp Ix, and then I get my Iz. And you're supposed to now recognize that this is a rotation. It's a rotation of Z about X. So you actually need line 2 from table 7.1, and that's the identity that I've written out there. And all you need to do is to put theta is equal to omega 1 Tp, and then you can use that identity. So that enables us to work out what happens. So let's just go over that again. So this is the one that we're trying to solve. We're going to use this identity, and we notice that we have to put theta equal to omega 1 Tp. And so the density operator at time Tp is cos theta, which is cos omega 1 Tp Iz, minus sine theta, which is sine omega 1 Tp Iy. And so that enables us to work out what's going on, and you can simplify this a little bit by realizing that omega 1 Tp is actually the flip angle alpha, right? Because it's the omega 1 field times the duration of the pulse that gives you the flip angle. So our final result is after the pulse we've got cos alpha times Iz minus sine alpha times Iy. Now, if you wanted to be a bit more condensed about that, you could write that in the following way in the arrow notation. Remember, we write rho 0 on the left, which was Iz. We write the Hamiltonian times time over the arrow. So the Hamiltonian was omega 1 Ix, and the time was Tp. And on the right, that's the solution we came up with. And again, if I use alpha as omega 1 Tp, you can just simplify it slightly to that. Now, what's the interpretation of this? Well, it just says that the magnetization is rotating in the ZY plane. And for example, if we make the flip angle alpha equal to 90 degrees, we will get sine 90, which is 1, and cos 90, which is 0, and you'll just end up with minus Iy. So it's exactly the same thing as the vector picture. The magnetization, which starts out, is rotating in the YZ plane, giving you oscillating Y and Z components, and after a 90-degree rotation, for example, it ends up on minus Iy. So this has produced, again, exactly the same result that we had from the vector picture. Now, we haven't quite finished this yet because, remember, we're doing the pulse acquire experiment, and so far we've only described the effect of the pulse. And we now need to describe what happens during the delay, where we have the free precession delay. So let's do that part. So during the free precession delay, the Hamiltonian is different, right? The Hamiltonian for free precession is omega Iz. And we need to consider the effect of this term on both the term in Iy and the term in Iz. Well, the term in Iz we don't need to worry about, because if we do a Z rotation about Z, nothing happens. So that term is unaffected. And now we need to do the term in Iy. And you need to look at this quite carefully. So there we are on the left, minus sine alpha Iy. That's the term in Iy. And I need to rotate that through the Hamiltonian times time. So that's omega Iz times the time t. Now, I've written out there in red, I've taken out the minus sine alpha as a factor, because this is just a number, and it's not going to affect the result in any particular way. It's just going to carry forward as a factor in the calculation. So ignore the bit in red, just look at the term there in black, and you'll see I got that by taking line 6 from the table, which is the rotation of y about z. And if you rotate y about z, you get cos theta Iy minus sine theta Ix. And all I've done is I've put theta equal to omega tau. So the thing in the square bracket is the new term, and the minus sine alpha is just a term that's carried forward from the original part of the calculation in a harmless way. So that's given us what we want, and as I said, the term in Iz is unaffected by the free precession, because free precession is a rotation about z, and if you rotate about z, nothing happens. So at the end of all of that, we've got something quite simple. After the pulse, we've got this mixture of z and y, and then after free precession, we've got this term, the cos alpha Iz, which didn't evolve during the free precession, and then the Iy term, which has evolved into a y term and an x term. And that is, of course, exactly what you would have expected from the vector picture, because if I rotate through an alpha degree flip angle, you end up with a minus y component proportional to sine alpha, and then that y magnetization rotates towards x when you have free precession, and that's exactly what that sine omega t times Ix is. So this quantum mechanical calculation predicts that you have an oscillating y component that goes as cos omega t, you have an oscillating x component that goes as sine omega t, and each of these terms has a magnitude sine alpha, depending on the flip angle, and there's a z component left over, which has magnitude cos alpha. And this is identical to what you'd come up with during the vector model. So this is the key point. So I now want to use the same approach to analyze the spin echo. Now you remember, in the vector picture, we had shown that the spin echo has this very special property that no matter what the value of tau is, and no matter what the value of the offset omega is, if the magnetization ends up on the plus y axis, right? And that we say that the offset is refocused. And what I want to do now is to basically show that same result, but this time using the operator method, again just to reinforce how the two things are connected. Now, in fact, we've already done a lot of the work, because we just worked out what happened if you did an alpha degree pulse followed by a delay t. And now what I want is a 90-degree pulse followed by a delay tau. So all I have to do is put alpha to pi upon 2, and put t to tau, and I will end up with what I want. And so without doing any calculations extra, at the end of the first time tau, I've got minus cos omega tau iy and plus sine omega tau ix. And that's just saying that after time tau, the magnetization has rotated through an angle omega tau away from minus y towards x. So that's that part. So now we need to consider the next element in the spin echo, which is the 180-degree pulse. And this is a 180-degree pulse about the x-axis. And that means immediately we need to worry about the term in ix, because a rotation about x will have no effect on that term. So first of all, we can forget about, for the moment, the sine omega tau ix term. And we only need to worry about the cos omega tau iy term. And I'm going to imagine that the duration of the 180-degree pulse is t pi. So we need to know the Hamiltonian and we need to know the time. So here we are using the arrow notation. On the left of the arrow, minus cos omega tau iy, which is what we start with. Over the arrow, the Hamiltonian times time. And the Hamiltonian is little omega 1 ix, because it's an x pulse. And the duration of the pulse is t pi, as I just said. And that is a rotation of y about x. And that is line 1 from the table. And that's shown at the bottom of the slide. If you rotate by an angle theta about the x-axis of something along y, you get cos theta iy plus sine theta iz. And you just look up that in the table. And all you have to do is to put theta equal to omega 1 t pi, and that's what's shown on the right-hand side of the arrow. And of course the term minus cos omega tau, that just carries forwards as a factor in a harmless way. So we've done the 180-degree pulse, which has given us that. But actually it's a bit simpler than this, because you remember that the flip angle of the pulse is going to be 180 degrees. So that means that omega 1 tau pi is going to be pi. So I can make that substitution. And of course cos pi is minus 1 and sine pi is 0. So that term on the right, the term in iz is actually goes to 0 because it's multiplied by sine pi. And so all I'm left with is cos omega tau iy. So the effect of all of this, in a rather long-winded way, is to say that all that the pi pulse actually did was it inverted the term in iy. And again, from the vector model, that should be no surprise to you, because if you think about, if you have a vector along iy and you rotate it by pi about x, it ends up on the other side of the axis. And that's all that's happened here. So we've now done the effect of the 180-degree pulse. So if we gather together where we are, we've got that term cos omega tau iy, which is the term we were just fiddling with. And we've also got this term sine omega tau ix. That was the term which wasn't affected by the 180-degree pulse. So now we've got to the end of the 180-degree pulse. Now in the spin echo, the next thing is a delay tau, and we've got to consider what the effect of the delay tau is on both of those terms. And so first of all, I'm going to do the term cos omega tau iy, and to save writing, I'm just going to set aside the cosine omega tau, not keep on writing that, just keep that in the back of my mind and put it back in at the end. So we've now got to work out what happens during a delay tau to the term iy. Right? So using the arrow notation, iy is the starting position. Over the arrow is the Hamiltonian times time. And the Hamiltonian is omega iz. and the time is tau. Because remember, this is free precession now. And that is therefore a z rotation of y. And you can look that up in the table, and a z rotation of y gives you cos theta iy minus sine theta ix. And all we have to do is replace theta by omega tau, and that's what we get. Now we'll do the ix term, and again we'll just set aside the sine omega tau term and pop that back in at the end. And it's exactly the same thing. It's a z rotation of x. And so we're going to get cos omega tau ix and sine omega tau iy. So again, you can look that up from the table. So now we've allowed these two terms to evolve during the second delay tau, and we can put it all together, and remembering to put in those factors of cos omega tau and sine omega tau that I had from the beginning. So the first term comes from the cos omega tau iy, and that evolves into an iy and ix. And the second term comes from the sine omega tau ix, and that evolves into an ix and an iy term. And if you look at those, you'll see that the two terms there in ix are going to cancel. One is minus sine cos, and the other one is plus sine cos. So the two terms in ix go away. And that just leaves the term in iy. And if you look at that, you'll realize that this is cos squared plus sine squared times iy. And cos squared plus sine squared is 1. It's one of those useful identities. So the answer is iy. And you knew that was what the answer was going to be, because from the vector model we worked out that at the end of the second delay tau, the magnetization appeared along the y-axis, and that's exactly what this calculation says. So again, we've used the quantum mechanical approach using these rotations in order to give us the same result. And every step, all we're doing is repeatedly applying these identities from this table. Now, we need to do this in a way that's less laborious, because if it was this laborious to do a spin echo, we would have given up a long while ago, right? And once you start doing these calculations, you realize that you can skip through a lot of the details. So for example, if you're doing 90-degree pulses, things are quite a lot simpler, because you always get a cosine and a sine term. But of course, cosine 90 is 0 and sine 90 is 1. So the effect of 90-degree pulses, you can usually just write down without fiddling around looking in the table. So if you take iy and you do a 90-degree pulse about x, you just get iz. Right? Of course, in principle, you get cos theta times iy and sine theta times iz, but theta is 90, so you only get the z term. So for 90-degree rotations, you can often just write down the result without referring back to the table. So that's one thing you can do. And in fact, 180-degree pulses are even simpler, because cos of 180 is minus 1 and sine of 180 is 0. So basically all that 180-degree pulses do is flip a few signs around. So for example, if I take iy and I do a pi pulse about x, it becomes minus iy. If I do iz and I do a pi pulse about x, it becomes minus iz, and so on. So again, once you get the hang of this, you don't laboriously go through every step of writing out the pulse as having an arbitrary duration. You just go usually immediately to the final result. So that will save time. The other thing that will save time is to really utilize this geometric interpretation. I've constantly referred back to the vector model to say that these operators are really doing the same things as the vectors. And I've also emphasized that all of these quantum mechanical identities that we've been using are actually rotations. So if you look at table 7.1, all of these things you can interpret as being rotations in a special kind of operator space. So for example, this identity e to the minus I theta ix, iz, e to the plus I theta ix, I can interpret that as a rotation of z about the x-axis, right? So the operator being rotated is iz, the one in the middle, and the axis that I'm rotating about is ix, and I'm rotating through an angle theta. And I can interpret that in a three-dimensional picture here, where the axes are not labelled x, y, and z, but are labelled ix, iy, and iz. I start on iz, I rotate about ix, and that rotates me towards minus iy. And that's all that that identity says. So all of these identities can be interpreted using this geometrical picture. And it's geometrical, but the axes are not labelled x, y, and z, they're labelled ix, iy, and iz. And in fact, if you look at these rotations from the table, you'll find that they all have a particular form. That if you rotate a given operator, just call it A, you always end up with A multiplied by the cosine of the angle. And you get a new operator, as let's call it B, multiplied by the sine of an angle. And all of those identities look like that. They're all cosine of what you started with, and then sine of some new operator. And so, if you think about this diagram, when we rotated about x, we ended up with cos theta iz, that's cosine of the angle times the old operator, and then minus sine theta iy, that's sine theta times the new operator. So all of these rotations have this constant form. So I would encourage you never to use the table, but always to use this diagram, because this diagram summarizes the results of the table in a form that's much easier to understand. So let's look at A to start with. Look at this one here. This is for rotations about x. So if I start on z and I want to rotate about x, all I do is I look on this diagram. Here I am, I start here on z, I rotate about x, and this tells me that I go towards minus y. And that tells me that if I rotated by an angle theta, I'd get cos theta times the old operator, iz, plus sine theta times the new operator, which is minus iy. If, for example, I wanted to rotate minus z about x, the diagram tells me the new operator would be iy. So it would be cos theta times the old operator, minus iz, plus sine theta times the new operator, which is iy. And likewise, these other diagrams, these describe to you what would happen if there was a rotation about z or a rotation about y. It's always cos theta times the old operator and sine theta times the new operator, and these diagrams will tell you what the old and the new operators are. And after a while, these things are just imprinted in your mind, and you don't even need to look at them. But to start with, I suggest that when you do these calculations, you have this diagram to hand so that you can see what's going to happen to all the operators, because actually that's all you need to know. So let's put that to use and analyze finally one more pulse sequence, and this is the 1-1 bar sequence. Now, this pulse sequence consists of a 90-degree pulse about x, followed by a delay tau, and then you do a 90-degree pulse about minus x, and then you acquire the signal. Now, we've already worked out what you get if you do 90-degree x followed by a delay, because that was the first part of the spin echo. So I can reutilize that. I get minus cos omega tau iy and sine omega tau ix. In other words, the vector has rotated in the xy plane. Now I need to know what happens if I do a 90-degree minus x pulse. Well, if I do an X pulse, all I need to do is look at figure A, which is this one here. And I need to know what's going to happen to this term and this term when I do an X pulse. Now, of course, the term in Ix is going to be unaffected, because if I rotate X about X, nothing happens. So the term sine omega tau Ix is going to be unaffected. What about the term cos omega tau Iy? Right, well, here we are. I'm at minus Iy, and I want to rotate about X. Actually, I want to rotate about minus X, so I have to go backwards in this diagram, and a 90-degree rotation will take me to plus Z. If I wanted to rotate about plus X, I would go down here to minus Z. So all that happens to this term, minus Iy, if I rotate about minus X, it goes to plus Iz. And that's it. So that's the answer. Now, you can just read that off the diagram, because of course if you're doing a 90-degree pulse, you just go one click round the diagram. And the result is that the magnetization, there's a cos omega tau term on Iz and a sine omega tau term on Ix. And in fact, this pulse sequence has been used for exciting signals in the presence of a strong solvent line. So for example, if you had a very strong line in the spectrum which was swamping the spectrum and you didn't want to excite it, you could put that on resonance, in other words with omega equals 0, and therefore the excited magnetization sine omega tau times Ix would be 0. So the on resonance signal will not be excited. But you could arrange it that other signals, in fact, in particular ones with omega tau is equal to pi upon 2, they would be excited along the x-axis with maximum intensity. So for example, you could arrange the amide signals or something like that with different offsets were excited, whereas a water signal was not. So this is actually a practical pulse sequence for exciting a spectrum in the presence of a strong line. And that brings us to the end of this first part about product operators.